Well, another interesting topic that we have to review is the formulation of Maxwell's equations with electric and magnetic sources. We have seen before that in nature there are no magnetic monopoles, but that they are mathematically possible, and also they are physically desirable because they are necessary to prove the quantization of electric charge, which is a known fact in physics. So we just modify Maxwell's equations adding magnetic sources. Here M is the magnetic current and tau is the magnetic charge volume density. So, in the same way as in Ampere-Maxwell equation, the curl of H is the electric current density plus the time derivative of the electric field or electric displacement vector, the Faraday equation is modified adding this magnetic current, so that both equations are now dual to the other. Since we have a minus sign here for the in the integral version for the derivative, the time derivative of the magnetic flux, now it is the time derivative in differential version, the time derivative of the magnetic field. Here we have a minus sign. We need to put also a minus sign here to make the equation consistent. But essentially, apart from the minus sign, the two equations are dual. Also, in the same way as we have that the divergence of the electric displacement vector is equal to the electric charge density, the dual one is that the divergence of the magnetic field, B, this is B, is equal to the magnetic charge density. Now, the set of Maxwell's equations is much nicer because it's symmetrical, and two of the equations are dual to the other two. In the integral version we have the same thing, and we put the magnetic or minus the magnetic current and the magnetic charge at the same locations as we did in the differential version of the equations. Now we must be able to solve Maxwell equations having electric and magnetic source. Solving the equations means that given a set of sources, we have to be able to compute the fields, electric and magnetic fields. Later I will show you how to solve Maxwell equation by using potentials, wave equation, Green's function, etc. I'll show you how to compute the electric and magnetic field from an electric current. Since electric charge is related to electric current through the continuity equation, for us it is enough to define the electric current, and the electric charge will be computed from the divergence of the electric current using continuity equation. So when I say sources, I mean both electric and magnetic currents. I mean both electric current and electric charge, or in the magnetic case, magnetic current and magnetic charge. But from a practical point of view, it is enough only to know the current. Well, we have to be able to solve Maxwell equations having both electric and magnetic sources altogether. We do this by superposition. We separate the sources, electric sources here, J and rho, electric current and electric charge, and we set the magnetic sources equal to 0 in this blue color box. And then in the green color box we set the magnetic sources, M and tau, and the electric sources are 0. Okay, so we have separated the problem in two. The problem in the blue box is an electric problem with electric sources. The problem in the green box is a magnetic problem with magnetic sources. The solution to the electric problem is is given by electric field 1 and magnetic field 1. The solution of the magnetic problem is electric field 2. Let's repeat. The solution of the electric problem is electric field 1 and magnetic field 1. The solution of the magnetic problem is electric field 2 and magnetic field 2. Of course, the original equations here are the superposition of the equations for the electric problem plus the equations for the magnetic problem. If we sum the equations in the blue box plus the equations in the green box, what we get is the original equations having both electric and magnetic sources. Okay? So by superposition, if the original equations are the sum of electric equations plus magnetic equations, then the overall electric and magnetic fields are the sum of electric and magnetic field 1 due to electric sources plus electric and magnetic fields 2 due to magnetic sources. So we have to solve separately the electric and the magnetic problem with electric sources and with magnetic sources, respectively. We know how to solve the electric problem. I will show you later how to compute the electric and magnetic fields due to electric sources, but this is something that is known and has no difficulty. And then we need to know how we can compute the solution of the problem with magnetic sources. It's very easy because the equations for magnetic sources, the equation in the green box, are dual to the equations in the blue box. These two sets of equations are dual. And therefore, by duality, we can solve the electric problem, and by duality, obtain the solution for the magnetic problem. How can we do this? Okay, we know that the sources of the magnetic problem are dual to the sources of the electric problem. Then, the solution of the magnetic problem must be dual also to the solution of the electric problem. So, what we do is we substitute the magnetic sources by the dual ones, the electric ones. Okay? And we substitute the sources using this duality table. The magnetic current is substituted by the electric current, and the magnetic charge is substituted by the electric charge. Then we solve the dual electric problem. This is something that is known how to, you will know in a few, 1 hour later you will know how to solve it. So it's known. We solve the dual electric problem, and then when we obtain the solution of the dual electric problem, we replace the dual quantities, that we replace the field by the dual ones, so we obtain the solution of the magnetic problem. And how can we substitute the fields by the dual ones? Using again the duality table. The duality table, we substitute the electric field of the magnetic problem by minus the magnetic field of the electric problem. So, sorry, this is the reverse. What we know, we have solved the dual electric problem. So we substitute the electric field of the dual electric problem by the magnetic field of the original problem. And we substitute the magnetic field of the dual electric problem by minus the electric field in the original magnetic problem. Okay? And why this minus? This minus comes from this. Let's erase the mark. Okay. The minus signs comes from this minus sign here. In the if we compare these arrows show the equations that are dual. We have solved the electric, the dual electric problem, and we replace the magnetic field of the electric problem with minus the electric field of the magnetic problem. The electric current by the magnetic current and the electric field by the magnetic field. And this minus sign goes to the other side and becomes these two signs here. So this minus sign here is very important because it is the minus sign that makes consistent the Faraday law of one problem with the dual Ampere-Maxwell law of the dual problem. Okay? For the others, there are no problems with signs here. These two, well, in this case, we see the need of the minus sign. The electric field of the electric problem is replaced by the magnetic field of the magnetic problem, and the magnetic field of the electric problem, notice the minus, is minus the electric field of the magnetic problem, which we can see here. Okay? And for the divergence equations, there are no problem. Electric field replaced by magnetic field, electric charge by magnetic charge, and magnetic field by minus electric field. But since it is equal to 0, the minus disappears. Okay? So at the end, the only thing that you have to know is this table. This table is the only thing that you have to know. And in fact, this table is very easy to remember because it's very trivial. The electric quantities are replaced by magnetic quantities and vice versa. So magnetic permeability is electric permeability, and the opposite also is true. Okay? Electric charge replaced by magnetic charge, electric current by magnetic current, electric field by magnetic field and vice versa, but with the minus sign. The only thing is that you have to know where the minus sign goes, in this case or in the other. And it is very easy to remember. Observe. When the field is of the same kind as the problem, magnetic field in magnetic problem is replaced by electric field. Magnetic field in magnetic problem is replaced by electric field in electric problem. Positive sign. Same field as the problem, or same kind of field as the kind of problem. Magnetic field in magnetic problem and electric field in electric problem goes with the same sign. And when the field is different than the problem, electric field in magnetic problem and magnetic field in electric problem, then there is the minus sign. Then the sign is reversed. Okay? So this is the rule of thumb to know when you have to use the minus sign or not. So using this trick of using duality, the duality table, what we get is the solution of the magnetic problem, E2 and H2. Now we have the solution of the electric problem, which was computed conventionally. We have the solution of the magnetic problem that has been solved using duality and solving in fact the dual electric problem. And then we obtain the overall solution summing E1 and H1 with E2 and H2. That is the solution of the electric problem plus the solution of the magnetic problem. So now you know how to deal with electric and magnetic sources and how to obtain the solution with them in Maxwell's equations. The following topic to review is boundary conditions. Imagine that we have two different materials, one material with some dielectric and magnetic properties epsilon 1, mu 1, and also possibly with a different conductivity, and then different medium 2 with epsilon 2, mu 2, and sigma 2 for the conductivity. Okay, then the fields will be of course different, and we will call fields 1 the fields in medium 1 and fields 2 the fields in medium 2. We will see that in order to support the discontinuity between the fields, a set of surface currents and surface charge will appear at the surface of the interface that separates the medium in order to support the discontinuity between fields 1 at medium 1 and fields 2 at medium 2. In order to formulate the boundary conditions, we use the Maxwell's equations in integral form that are these. The flux of the electric displacement vector is equal to the enclosed electric charge. The flux of the magnetic field is equal to the enclosed magnetic charge. The circulation of the auxiliary field H is equal to the current plus the time derivative of the electric flux, and the circulation of the electric field is equal to minus the magnetic current minus the time derivative of the magnetic flux. All this is known from Maxwell's equations in integral form. So we apply these equations to some differentials, volume and surface. We apply the two divergence equations to a differential volume in the shape of a small cylinder. The height of the cylinder H is almost zero, is infinitesimal, and then we can easily observe that the total flux of the electric and magnetic fields through the surface is equal to the flux through the caps, because the side surface is zero, since the height of the cylinder is zero. And we see if the cylinder is differential, then there is a very small surface cap, and essentially the total flux becomes the subtraction between the electric field normal to the surface in medium 1 minus the fields in the normal to the surface in medium 2. And I say minus because the unit normal to the surface are opposite. So what we get from the Gauss equations, the Gauss laws applied for electric and magnetic case, applied to this differential volume in the shape of a cylinder, what we get is that the difference between the displacement vector in medium 1 minus medium 2 and normal component is equal to the surface charge in the surface that separates the medium. And it is the surface charge density, because we have when we compute the flux, we have the surface of the caps multiplying the fields, and the surface of the caps goes to the other side dividing the charge here. So what we get is the surface charge density. And the same for the magnetic case, but in this case it is a magnetic charge density. I have not done the derivation in detail. I have just made a very short and very brief sketch of the derivation, because the derivation is well known. You should know this derivation from your previous courses on magnetic fields or electromagnetism, and it is also in the book by Griffith that I recommended you, and in the book by Balanis that I also recommended as reference. So I am just sketching the derivation, but what is important is the result. And the result is that the difference in the normal component of the electric or the magnetic fields is equal to the surface charge density, electric or magnetic, depending if it is electric field or magnetic field. And in the case of electric field, it is not actually the electric field, but the displacement vector, which is epsilon times the electric field. The same as in the dual case, the magnetic field is mu times the H auxiliary vector. Okay, this is well known. And then we have similar laws for the Ampere-Maxwell and Faraday laws. In this case, we apply the integral form of Ampere-Maxwell and Faraday's laws to a small infinitesimal surface in the shape of a rectangle, and then the height of the rectangle goes to 0, so the circulation of the electric and the circulation of the magnetic field is essentially equal to the value of the field at the top side of the rectangle minus the bottom side of the rectangle multiplied by the length. By the length goes dividing to the other side, so you get the current divided by the length of the delta L is the length of the rectangle here. You get the current divided by the length, which is in fact the surface current density. So that what you get is that the tangent component of magnetic field in medium 1 minus the tangent component of magnetic field in medium 2 is equal to the electric surface electric current, the surface density of electric current. And when I say magnetic field, I mean magnetic auxiliary vector H, because it is the one that you have in ampere Maxwell equation, okay? And the same from Faraday equation, we similarly get that the difference in the tangent component of the electric field minus the tangent component of the electric field in medium 1 minus the tangent component of electric field in medium 2 is equal to the magnetic charge with reverse sign, with minus sign that comes from this minus sign here. And I say the tangent component, but it is not actually the tangent component, but it is n times the magnetic field, which is in fact the tangent component, but you have to take into account that this n, this product with n, in fact rotates the tangent component. So if the tangent component is this multiplication by n gets in fact the normal to the tangent components like this, okay? But anyway, it's essentially a tangent component. In fact, you get the tangent component if you rotate 90 degrees the current, okay? Well, all this is well known, but the result is that when there is a discontinuity, there are surface charges and densities at the boundary that support the field or flux at the discontinuity. And the same is valid for discontinuities of the field in free space. There is an important case. Important case is when one of the two media is a conductor. For example, if medium 2 is a conductor, then what we get is that fields at medium 2 are equal to 0, because you know that in a steady state the fields inside a conductor are equal to 0. So what we have to do is to replace the fields in medium 2 here. We have to replace let's try another color. We have to replace the fields in medium 2 by 0, okay? And what we get is then that the tangent components of the electric and magnetic field are equal to the surface current densities, and the normal components of the fields are equal to the volume charge densities. But we have to take into account that in an electric conductor only electric currents and electric charges can exist. So in an electric conductor the magnetic current is equal to 0, this is 0, okay, and the magnetic charge is equal to 0. So the only thing that remain are the electric current and the magnetic current. So in an electric conductor we get the well-known boundary conditions that the tangent component of the electric field is equal to 0, the tangent component of the magnetic H field is equal to the electric current density, the normal component of the electric displacement vector is equal to the volume charge density, and the normal component of the magnetic field is equal to 0 in an electric conductor. But in a magnetic conductor we have the opposite. In a magnetic conductor the electric current is equal to 0 and the electric charge is equal to 0, okay? So we get 0 here. And of course the magnetic current and the magnetic charge are different than 0 in a magnetic conductor. So in a magnetic conductor, the equations that we get are exactly the dual of the equations for the electric conductor. But we can get the equations for the magnetic conductor just applying the duality table. I will not repeat which are the tangent components of the fields in the magnetic conductor, because it is as easy as use the duality table and get the dual of what I said before about the tangent components of the field in the electric conductor. When there is a dielectric, a discontinuity between two dielectrics, then in the discontinuity between two dielectrics, there are no sources at the boundary, so all the sources at the boundary are equal to 0, and we get the same boundary conditions, but now at the right hand side we have 0 everywhere, because in a dielectric you cannot have a net sources. You have polarization and magnetization sources, but they cancel out, and there are not net sources, okay? So what you get is that the tangent components of the electric field are continuous at the boundary, and the tangent components of the magnetic field are continuous at the boundary. That is, the tangent component of the electric and magnetic field in medium 1 are equal to the tangent components of the electric and magnetic field at medium 2. So there is a continuity in the tangent components of the field. So here I say that the tangent components of the fields are continuous, okay? But what happens with the normal components? The normal components that are continuous are the normal components of the displacement vector and the magnetic field B. But this means that since D is epsilon E and B is mu H, what we get is that the tangent component, sorry, not the tangent, the normal, because they are here considered normal components. The normal components of the electric field are not continuous, because epsilon 1 is different than epsilon 2. The normal components of the displacement vector is continuous, but the normal component of the electric field is discontinuous, okay? And the normal component of the magnetic field B is continuous, but the normal component of the auxiliary field H, that for us, for engineers, we usually call H a magnetic field, then the normal component of magnetic field H is discontinuous, because mu1 is different than mu2. So here, in the case of dielectrics, and considering that the fields are E and H, we have that there is a continuity of the tangent components of the field, continuity of the tangent components, and discontinuity of the normal components of fields E and H. Well, in the previous slides regarding boundary conditions, we have been talking about materials having an epsilon and a mu. And let us just remind you about the physical meaning of that epsilon and mu that define the electric and magnetic properties of materials. If we have a dielectric material and we apply an external field to the material, what happens is that if we have a lot of dipoles inside the dielectric material with random orientation, the electric field orientates the dipoles so that all the dipole moments are aligned, and then when we sum up all the aligned dipole moments, we get an overall sum of these dipole moments that if we divide by unit volume, we get a polarization, what we can define a polarization vector. This polarization vector is just the sum or integral of all the microscopic dipole moments of the aligned molecules inside the dielectric over the volume. That is the volume density, is the volume P is the volume density of dipole moments, and we call P polarization vector. If the molecules inside the dielectric are not polarized, it is the electric field that polarizes the molecules and then orientates the dipoles. Okay? So the net effect for us, the important thing is that there is a net polarization vector. This polarization vector produces electric field. So we have to take into account this effect, and since we define the displacement vector equal to epsilon 0 electric field in free space, in a dielectric media we have to add the polarization vector to compute D. And then in linear media the polarization vector is proportional to the applied electric field, not the external field but the overall field, which is the external field plus the induced field due to the dipoles. Okay, so this is the definition in fact of a linear media. Linear media is that media such that the polarization vector is proportional to the total electric field in the media. So we define this constant called electric susceptibility, which is the constant the constant of proportionality between P, polarization, and epsilon 0 E. Okay, so we substitute a P by this, and we get epsilon 0 out, the sum, and what we get here is a scalar quantity, but that we call relative epsilon, and we define epsilon, the overall epsilon, as the ratio between the displacement vector and the electric field. And it will be equal, as we have seen here, to epsilon 0 times the relative epsilon, the relative permittivity, and relative permittivity is 1 plus the susceptibility. So now we will not consider anymore the microscopic dipoles inside the dielectric nor the polarization vector. We will just work with this equivalent epsilon. We will work with this equivalent epsilon, which will be the constant of proportionality between D, displacement vector, and E. Okay, and often we will use also the relative permittivity. Well, in magnetic materials we don't have dipole moments, and we don't have polar molecules and dipoles. Then dipole moments, what we have is electrons. Imagine an electron here. This is an electron. We have electrons spinning around nuclei, and a moving charge is a current. So these form current loops. And you know that a small current loop has a magnetic dipolar moment. So for each atom we have, or for each spinning electron better, we have magnetic dipole moment. And this is a differential. Okay, you know that the dipole moment of a current loop is equal to the current times the surface of the loop, and with the direction of the unit normal to the surface. And this is a differential of magnetic dipole moment, and when we sum or integrate for the whole material and compute the density of magnetic dipole moment per unit volume, okay, what we get is the magnetization M. So magnetization M is the density of magnetic dipole moment the volumetric density of magnetic dipole moment, and it is the dual to the polarization P, which is the volume density of electric dipole moment. So this magnetic polarization vector M, but that I repeat is related to the magnetic dipole moment, is due to the alignment of all the electron spins. When we apply a external magnetic field, we get the dipole moments aligned parallel to the magnetic field in the same way as electric dipole moments in dielectric materials are aligned parallel to the electric field. So in this case, when all of them are parallel, the small or microscopic magnetic dipole moments do not cancel out, as happens when they are randomly oriented, as in a material with no magnetic field. When there is no magnetic field, of course the orientations are random, the magnetic dipole moments cancel out, and the sum M is equal to 0, okay? The sum M, remember, is the sum of all the dipole moments, and then the sum over divided by the volume to get the density of per unit volume, okay? And then when we apply an external magnetic field, we get all the dipole moments oriented parallel to the magnetic field, and they sum, and then we get a magnetization different than 0, because all of them are aligned and sum parallel vectors. And this is completely the dual of what we get with in the dielectric case with the polarization. The same as we did for electric media, we define the magnetic field B in free space as mu0 h. H is the auxiliary vector, and in the magnetic media will be the same thing, mu0 h plus the magnetization M. But in this case, we multiply by mu0. And we define magnetic linear magnetic media as such media, as that media where the magnetic polarization is proportional to the total magnetic field H, and the proportionality constant is the susceptibility. The magnetic susceptibility is the ratio between the magnetic polarization M and the magnetic auxiliary field H. So we do the same thing as we did for in the dielectric case. We substitute the magnetic polarization by the linear media formula, and what we get is that the magnetic field B is equal to the magnetic auxiliary vector H times a magnetic constant mu. The magnetic constant mu is equal to mu0 times the sum 1 plus magnetic susceptibility, the dual of what we get for the dielectric case, and we define relative magnetic permeability as the ratio of mu over mu0, so that the magnetic relative permittivity is equal to 1 plus the susceptibility. So this is the same as we get in the dielectric case, the dual formulas. But the important thing for us is this. The important thing for us is that B is mu h, okay, and that mu is what we use in engineering. It is a macroscopic constant that takes into account the effect of the magnetization of the material. And the same as in the dielectric case, in engineering we forget about the microscopic current loops, the microscopic magnetic dipole moments, and we use a macroscopic constant mu that takes into account all the microscopic or magnetization effects. Well, after we have modeled the properties of electric and magnetic materials existing in nature, such as dielectric materials, we model dielectric properties with epsilon in the electric permittivity, and magnetic materials, we model the properties of magnetic materials with mu, the magnetic permeability, equivalent ones. I must say something about materials not existing in nature, but materials that are artificially created. In fact, I have just cut and paste the definition, the starting paragraph in the Wikipedia entry about metamaterials, and it says that a metamaterial is any material engineered to have a property that is not found in nature. So this is very important, that we can achieve properties not found in nature. I will show you that, for example, we can create magnetic ground planes, because you know that from the previous boundary conditions, you know that in a magnetic conductor, the boundary condition requires the existence of tangent magnetic current and magnetic volume charge, surface charge density. And this magnetic surface current and surface charge density do not exist in nature, but that means that the magnetic conductor does not exist in nature. But we can artificially create a material that behaves as a magnetic conductor. So we can achieve properties that are not found in nature. How can we do that? Well, Wikipedia says that they are made from assemblies of multiple elements fashioned from composite materials such as metals, and in acoustics we could also use plastics, etc. But here we concentrate in electromagnetics, and in electromagnetics we use metals. Okay? Also dielectrics. Well, of course we could also use dielectrics, but essentially metals. For example, this is just an assembly of open loops and wires, and using this assembly of open loops and wires we can achieve equivalent permittivity and permeability that are not found in nature. But it is very interesting is that always the materials are usually arranged in a repeating pattern. This is very important, and very important also that the scale of the pattern is smaller than the wavelength. That is, the metamaterial looks like an array. Here you can observe the array of open loops and the array of wires. And what is very important is that the spacing of the array must be much smaller than the wavelength, and also the size of the elements must be much smaller than the wavelength. Okay? Not, of course, the length of the wires here, only the width of the wires and the separation. And since the elements are much smaller than the wavelength or the separation between them, the wavelength, the wave, sees not the individual microscopic elements, but the wave sees the bulk. What the wave sees is the bulk of materials all together, the resonance that they create all together. And this is what is important. And then, which is very important, that the properties do not depend on the properties do not depend on the properties of the base material, but from the newly designed structure. That is, the properties do not depend on the properties of the loop, but on the properties of the array. Okay, and this is very important. So we can create with this a material that is able to block, absorb, or enhance bend waves in a different way as the materials found in nature. For example, a very simple example. This is something that you already know from your antennas course. you know that we can simulate a sheet of metal, a ground plane, a sheet of perfect electric conductor. PEC means perfect electric conductor, okay? So we can simulate a sheet of perfect electric conductor with an array of parallel wires. And this array of parallel wires will reflect incident wave. If we have an incident wave like that, and the polarization, the electric field polarization is parallel to the wires, very important, in this case we have a reflection. If the incident field has polarization parallel to the wires, the wave is reflected by the wires, by the array of, not by the wires themselves, but by the array of wires. In fact, I think that there is, yes, some time ago I wrote an exam problem for the engineering physics degree in which they analyzed the array of wire and they proved that the factor array was responsible of the array factor, I mean, the array factor was responsible to from the reflection. It was the array factor that reflected the waves. Okay? And of course, since the wave is reflected, it is blocked and there is no transmission. Only for polarization parallel to the wires. If the incident polarization, these are the wires, if the incident polarization is perpendicular to the wires like this, then the field is transmitted through the array of wires. There is no reflection. So in this case, it depends on the polarization. But it is just a very simple case of metamaterial. Of course, what we have built is something that already exists in nature. But I only want to show here that we can build using an array, an assembly of small elements with a repeating pattern, an array in fact, we can build something that behaves the same as a bulk material. In this case, it's a material already existing in nature, a metal, a perfect electric conductor, and we use it, for example, for building reflectors like this. This is a dihedral reflector for a Yagi antenna. But we can build this because it has advantages over the bulk material, over the perfectly conducting sheet. For example, it has less weight or less resistance to wind, etc. But in the same way that we have built something having the properties of a perfect electric conductor, we can build an array having the properties of a perfect magnetic conductor. PMC stands for perfect magnetic conductor. In this case, it is not an array of wires, it is an array of open loops, but the behavior is equivalent to a bulk material consisting on a perfect magnetic conductor, with the properties of a perfect magnetic conductor. Of course, as I said before, the distance, the array distance between elements, the array separation must be much smaller than the wavelength. But with this, we can build ground planes for antennas. And the nice thing of a ground plane for antennas done with a perfect magnetic conductor is that if the reflection coefficient in a perfect electric conductor is equal to minus 1, in a perfect electric conductor, due to image theory that we will review in chapter 2, the reflection coefficient is minus 1. In contrast, in a perfect magnetic conductor, the reflection coefficient is equal to 1. And this is an advantage for building antennas. So this is just a possibility for building antennas. But we can do much more. We can create materials having permittivities and dielectric permittivities that are negative and magnetic permeabilities that are negative, that of course cannot be found in nature. But these materials with negative epsilon and mu that are called double negative material, double negative because both quantities are negative, have non-physical properties very interesting. And for example, the propagation is negative in the sense that the wave velocity is negative. The wave velocity is opposite to the group velocity and the velocity of energy, and the direction of propagation or the direction of phase velocity is opposite to the direction of the propagation of energy. And this can make very funny effects such as a refraction in the opposite way, and many interesting things, like for example an invisibility cloak. For example, what is an invisibility cloak? We imagine that we have a perfectly conducting cylinder. This is a metal cylinder, okay? We have an incident wave here. Let's use another color, a black color. We have an incident wave here, okay? Then the wave is reflected, and for that reason we can see a standing wave. You can see here the standing wave, okay? You can see here a standing wave. This is due to the sum of the progressive incident wave and the regressive reflected wave that produces a standing wave. You can see a block here, a shadow region where the field is almost zero. This is the shadow here, a shadow cone, okay? This is shadow. And this is what happens due to the effect of the diffraction at the cylinder. This perfectly conducting cylinder reflects the incident wave, blocks the incident wave, and produces a perturbation in the electromagnetic field, in the electromagnetic wave. And for that reason, we are able to see the cylinder. If this electromagnetic wave is optical, we are able to see the cylinder because we see the reflected wave here. Our eye sees the reflected wave, or we can see the shadow region here. Okay, and this allows us to see the cylinder. But we can cloak the cylinder and make it invisible if we surround the cylinder with that. We surround the cylinder with a sheet of a metamaterial having epsilon and mu, such that following the refraction laws, the wave is not reflected. There is no reflection here. This is the incident wave. These are the incident rays. So the incident rays are bent like this, and they exit like this. So this is the path followed by incident rays. Here and here and here. This is the path followed by incident rays. And there is no reflection. I just crossed the reflected field. There is no reflected ray. There is no reflection, and the overall field, incident field plus diffracted field, the overall field is almost the same as the incident plane wave. So we have cloaked the perturbation of the cylinder, and the cylinder is now any longer visible. If the total field is the same as the incident wave without the cylinder, then we cannot see the cylinder. Okay, we have an eye here observing. This eye sees no reflected, I cross it, no reflected wave, no reflected rays, and there is no shadow here. We observe from behind, we see no shadow. So we see just the incident field without perturbation. This is an invisibility cloak, and this is made on an array of small elements. Of course, the size of the elements must be much smaller than the wavelength. The separation between elements must be much smaller than the wavelength again, as I said before. And in this case, often the elements are a combination of open loops and wires, and in this case the wires are integrated at the ends of the open loop, okay? And the way to design this, we have to use a computer, and what we do is we optimize. We run a global optimization program, and we optimize the values of epsilon and mu, permittivity and permeability inside the metamaterial, and in order to get zero diffracted fields and total field equal to the incident field. And we do this just by a normal global optimization algorithm. And we get values of epsilon and mu, and then n. You know that n is 1 over square root of relative epsilon and mu. N is the refractive index. And we get values of epsilon and mu, and therefore n, that are not found in nature. Even they are of course complex, negative, everything you can find there, everything not found in nature. And we use the metamaterial to build this epsilon or synthesize this epsilon and mu. And to finish with materials, we have to remind the properties of conductors. You know that in conductors you have free electrons, and these free electrons can move along the whole surface of the conductor. So when you apply a field to a conductor, the electrons move and they produce a conduction current equal to the conductivity of the conductor times the electric field. If in Ampere-Maxwell equation we replace the current by the conduction current equal to the conductivity times the electric field, and we get the electric field out of the summation, we get this. And here, if we compare with the Ampere-Maxwell equation with no excitation current, we can assimilate this, we can make this parenthesis equal to an effective epsilon, so our effective epsilon is equal to the permittivity real part minus an imaginary part that depends on the conductivity. Okay, so this is the complex permittivity model of conductors that we use in engineering. Remember that in engineering we don't want to deal with the microscopic properties of materials like they do in physics. We work with equivalent epsilon and mu whenever possible, and in this case for conductors we have a complex equivalent epsilon where the imaginary part accounts for the effect of the conductivity. Okay, and it is interesting to remark that at very high frequencies in the optical case we have to, well, the frequency is so high that we have to account for the force necessary to accelerate the electrons, because you know that the electric field produces a force in the electrons. The electrons have to oscillate following the electric field. We are in time domain in harmonic regime, so we have a sinusoidal electric field, and the electrons have to oscillate following the electric field due to this equation and due to the force exerted by electric field in the electrons. But the electrons have inertia, they have a mass and have an inertia, and we have to account for Newton law, the third Newton law, force equal a mass times acceleration, and compute the acceleration of electrons and take into account the acceleration of electrons in the equation for the current. And we account for this, we get a different effective epsilon. It is also complex, but it is completely different. It depends on a resonant frequency and a relaxation time. This resonant frequency and relaxation time depend on the mass and charge of the electron because it depends on the force exerted by the electric field and the inertia of the electron, so it depends on the charge and the mass of the electron, and it is what is called plasmonic effect. You can study this in some physics book. I can give you information about this if you are interested in, but for my engineering point of view, the only thing that is important to us, the only thing from engineering point of view that is important to us is that we have a equivalent epsilon or effective epsilon, effective permeability given. It is also complex. It is given by a different formula from the conventional effective epsilon for a conductor at low frequency. Low frequency in this case is radio frequency, but for optical frequency the formula is different. Okay, this is the only thing that you have to know. If you are interested in how to compute the plasmonic resonance frequency and the relaxation time, there are lot of information about this. You can find, for example, in Wikipedia, but I can give you also information. It is, for example, it is given also in the electromagnetics course on the engineering physics degree. Well, now we finish with materials. I will record the remaining of this chapter 1 in a separate video. It took me longer than expected, so it is not 3 videos as I thought, but it will be 4 videos.